7.1 talks about orthogonal matrices. Definition: a square matrix A is said to be orthogonal if its transpose is the same as its inverse. So given matrix A, if I take the inverse and the transpose, I get them to be the same. Or you could, instead of finding the inverse, since that's a bit annoying if it's not 2 by 2, or you could equivalently take A, multiply it by its transpose, and take the transpose multiplied by A and get the identity matrix. That's how you check if they are orthogonal. A matrix transformation from Rn to Rn is said to be an orthogonal transformation or an orthogonal operator if A is an orthogonal matrix. So, remember, that's the linear transformation. Well, now those are very useful, both of those. These are the most used in our applications. The following are equivalent. Anytime you see that, anytime you see an n by n matrix, where the number of rows equal the number of columns, we call that a square matrix. A is orthogonal. If A is orthogonal, and that's something we're going to check because that's really what we're looking at. If A is orthogonal, well, the row vector of A, let's just simple, let's make it 2 by 2. The row vectors of A form an orthonormal set. These rows better be orthonormal. What does that mean? Well, 1, the dot product of those equals 0 and the magnitude equal 1. And also, the column vectors, if you look at that column and that column, they should be orthogonal and they should have a magnitude of 1 as well. So you could check that way quickly if A is orthogonal. Also, these are giveaway. The transpose of an orthogonal matrix is orthogonal. The inverse of an orthogonal matrix is orthogonal. A product of orthogonal matrices are orthogonal. So once you're given it's orthogonal, pretty much any combination of any combination of transpose, inverse, there are more. And if A is an orthogonal, then the determinant of A is plus or minus 1. That's important to get. So keep that in mind. Now this, we're going to play with this a bit. If A is an n by n matrix, then the following are equivalent. This is going to be used for our transformation. A is orthogonal, again, just like we have here. If A is orthogonal, then the row vectors are orthonormal and the column vectors are orthonormal. Also, if you take the magnitude of AX, you should get the magnitude of X. And if you take AX dotted with 8Y, you should get X dotted with Y, where X and Y are, of course, on Rn. Well, let's play with this just a bit, not a long section. So here we say, determine whether the matrix is orthogonal. Well, let's see. The magnitude is 1. The magnitude is 1. Okay, that didn't work. If I take the dot product, whether I take the rows or the column, it's 0. So that's not working. Call this A. One way of checking is, so I was looking for exception. If the magnitude of any row or column is not 1, automatically it can be orthonormal, and therefore, remember, orthonormal means they are orthogonal and the magnitude of each of those is a 1. Then automatically it is not. If these match, well, we're going to do the brute force, that is 1, 0, 0, 1. And if I take the transpose of that, that's also 1, 0, 0, 1. Well, that turns out to be 1 plus 0, 0 plus 0, 0 plus 0, and 0 plus 1. Okay, it checks, that's not enough. You're going to do this. And that is this first. Well, obviously it didn't change, right? That is still 1, 0, 0, 1, so yes. we say it is. If we called it A, we say A is an orthogonal matrix. And how about this vector? Well, I look longwise. I noticed that the magnitude of that is 1 4/5. Yeah, that's 1/4. That's, and that, yep, out of luck. I was hoping that will work. Well, okay, if I take A, call this A. If I take A and A transpose, that, oh, but I could tell the dot product of those is not 0, right? So they're not orthogonal. Yeah, if I take the dot product of the columns, that's not 0, so that's not satisfying that case, C, right? So I could say take I love it when it starts filling in the blanks itself. Okay, here. Therefore, A is not, and of course you could take A dot it. Oh yeah, the same thing. That's not gonna be I. You're gonna get something everywhere, right? But that's sufficient. So that's why those are so useful. I'm talking about these types. They say the following are equivalent. These are the ones that I use the most. Anytime I look at those, I take as much as I can. If A is orthogonal, take A times X. If they gave you X, you could do that too. Now, any of those will do. You don't have to do all of them. I'm looking at this, and I notice, okay, that's 1. And what is that? That is 1 over 3 plus 1 over 4. Oh, hey, look at that. If I take R2 and let me see, R2 magnitude is square root of 1 over 3 plus 1 over 4. That is 4. That's 7 over 12, which doesn't equal 1. So no. Call this A. A is not an orthogonal. No, A is not orthogonal. There you go. That's sufficient. Again, eyeball whatever you can. If these work, if you go vertically, 1/3, yeah, vertically, 1/4, 2/4, also that one right there, column 3, doesn't seem to work. Well, how about this? Show that the matrix, okay, so this is orthogonal. They're telling you that. Let's see. First calculate, so they want us to do all brute forces. Let's do all, that's fine. It's a good practice. That's all we want. So the goal is, given a matrix, can you tell if it's orthogonal? And that's important. Take A and multiply it by its transpose. Well, let's see how that works. That is 1/3, 2/3, -2/3. They're all fractions, so you gotta be, let me write that better. So you gotta work just slowly. Okay, 1/3, 2/3, -2/3, 2/3, -2/3, -1/3, 2/3, 1/3, and 2/3. You know what? I'm thinking, is that kosher? I'm thinking, why can't I just do that? I can. Now the transpose, Can you multiply that by 1/9? Now I'm playing it. So take this, and that is 1, 2, -2. The second, 2, -2, -1, and 2, 1, 2. Okay, I'm just trying to figure out. I'll leave the 1/9 out of it. And what am I looking at? Okay, so this with this. 1 plus 4. 1 plus 4 plus 6. 1. Oh, that's not working. Oh, no. Hold on. Let me check. 1, 2, -2, 2, -2. Yep. And that's a 2. Otherwise, I was going to say it's not, but then they told us to show it. So let me make sure I didn't mess up the other part. 1, 2. Okay, so let's see now. 1 plus 2, 1 plus 4 plus 4, 4, 8, that's 9. Very good. And for this one, 2 minus 2, 2 minus 4 plus 2, that's a 0. And for this one, -2 minus 2 plus 4 is a 0. Good. If I go for the second, 2 minus 4 plus 4 is 0. 4 minus 4, that's 0, plus 1 is, okay, oh, 4 plus 4 is 8, plus 1 is 9. Very good. And -2 plus -2 plus 2 plus 4. That's not working. -2 plus 2 plus 2. Okay, why is that not working? Let me check. That's negative. That's negative. And that's right. That is 2. Oh, no, not that one. That one. That is -4 plus 2 plus, that is 0. I was multiplying this. Okay, when I get to the third, I'm looking at -2 minus 2. That's -4 plus 4 is 0. I'm looking at -4 plus 2 plus 2 is 0. And the last one, I'm looking at 4 plus 1 plus 4, that's 9. So yeah, if you multiply those, that is the identity. It checks. Now, they only told us to check 8. Oh my God, I did it backwards. Okay, well, you only have to check what they tell you, right? I did it backwards. Obviously, if it works this way, it works the other way. I messed up. Now, theorem 7.1.1 and 7.1, they want part B and C, and we know what those are. Look at the first row. R1. Wait, did I put an arrow on that thing? Ah, look at that. So row 1, that is 1/3, 2/3, 2/3. If I take the magnitude of that, that would be 1/9 plus 4/9 plus 4/9. That is 1. The magnitude of R2, which is the oh, I forgot. Second row, well, obviously that is 4/9 plus 4/9 plus 1/9, which is 9/9, that's 1. And you could check the third, 4/9 plus 1/9 plus 4/9, that checks. Now, if I take the columns, if I take the magnitude of, oh, that's B. if I take row 1 dotted with row 2, row 1 with row 2, that is 2/9 minus 4/9 plus, that's a 0, good. And if I take R1 and dot it with R3, then that is, here, let me write it out, -2/3, -1/3, and 2/3. So that would be -2/9 minus 4/9 plus 4/9, that's 0. And if you take R2 dot it with R3, those two, that is -4/9 plus 2/9 plus 2/9, that's also 0. So they all check. Very good. That part is done. And if I go for the second part of 7.1.1, now you're going to check if the column vectors form an orthonormal. Well, look at the magnitude of each of those. So here, let me list them out. 1/3, 2/3, -2/3. 2/3, -2/3, -1/3, and 2/3, 1/3, and 2. And of course, the more important question is, how do you come up with an ortho? How do you make an orthogonal vector? So call that column 1. Okay, and obviously the magnitude of each of those is 1. And if I take the dot product, C1 dotted with C2, that is 2/9 minus 4/9 plus 2/9, that's 0. C1 dotted with C3, that is 2/9 plus 2/9 minus 4/9. And if I take C2 dotted with C3, 4/9 minus 2/9 minus 2/9 is 0. So yes, it checks. And there it is. Now, if any of those, when you look at a problem, eyeball which of those, and of course this is the most work, eyeball those. If the magnitude is not one of them, then hey, guess what? That's an easy problem to do. And here, let's check this, make sure we're getting that part out of the way. And let the transformation from R3 to R3 be with matrix A, and there's A right there, be multiplication by the orthonormal matrix. They're telling you this is orthonormal, you don't have to check. And exercise 6, so that's where I copied this from. It's right there. And your homework is going to say 5. Find TA of x for vector 0, 1, 0. So if I take TA of x, well, that is AX. That is, actually, yeah, that's fine. 1/3, 2/3, -2/3, 2/3, -2/3, -1/3, 2/3, 1/3, 2/3. And if I take that, and what would I get? 0 plus 2/3 plus 8/3, that's 10/3. For the second, I'll get 0 minus 2/3 plus 4/3 is 2/3. And for the third, I'll get 0 minus 1/3 plus 8/3 is 7/3. Okay, and if I take the magnitude of TA of x, that would be the magnitude of 10/3, 2/3, 7/3. That is the square root of 100 over 9 plus 4 over 9 plus 49 over 9. That's the square root of 100 and what is that one? 49, 150 153 divided by 9, 5. 9 divides 153 because if you add the digits, that's divisible by 9. 9 divides 14 one time, and you'll have 6 left. 63 7 times. Okay. And if we take the magnitude of x, that's the magnitude of 0, 1, 4. And as you see, it checks. Under what condition will a diagonal matrix be orthogonal? Okay, if we have a matrix n by n, and it's diagonal, whatever this letter is, I don't know, let's say L. Well, all of these not equal. They could be plus or minus. There's no specification. So how do you say that? You'll say all main diagonal entries must be plus or minus 1, right? And the reason for that, you want them to all have a magnitude of 1. If A is not 1 or negative 1, then the magnitude of that row or that column is no longer 1, and therefore it can be orthogonal. So you want all the main diagonal entries to be 1 or negative 1. And that's pretty much all we have to do for this section.